Suppose I have a conducting sphere, so spherical, solid spherical conductor, solid spherical conductor. And onto this little corner right here, I throw -5 microcoulombs. So first off, is -5 microcoulombs, is that a reasonable charge? Well, actually that is. If we soup up the Van de Graaff generator, the one that we have at school, it's in the microcoulomb range. If I take a piece of rabbit fur and a PVC pipe and I rub the PVC pipe with the rabbit fur, it's also in the nano to microcoulomb phase, depending upon several factors. And so this is reasonable. So I put -5 microcoulombs onto this, and so how many electrons is that? So it's like doing a conversion. Micro is 10 to the -6th. And then I multiply times, well, -1.6 times 10 to the -19th coulombs per electron. Coulombs will cancel out. Officially, it's not a conversion, but the math is very much like a conversion. And so what you end up with is 3.125 times 10 to the 13th electrons, 31.25 trillion electrons. Now, I know that these charges, when they're put here together, since electrons hate each other, they're going to try to spread apart, and they're going to try to get as far away from each other as possible. So they will go to the outside surface. Well, let's see how can we back that up? Well, we'll use Gauss's law here. So what I'm going to do is I'm going to create a Gaussian surface just inside the outer surface here. So this is a Gaussian surface, a Gaussian sphere more specifically. It is not a physical sphere, it is a virtual one, but we have it just inside the sphere there. I know that inside a conductor the electric field is 0. Gauss's law of electricity tells me that the electric flux through a closed surface is equal to the enclosed charge over epsilon sub naught. If the electric field is 0 inside here, where this dotted line is, then this has to be 0. That's equal to the enclosed charge over epsilon sub naught. Epsilon sub naught is a constant, it is not 0, and therefore the enclosed charge equals 0. So there is no charge, coulombs, there is no charge inside the sphere here. It's all on the outer surface. Sorry, let me rephrase that. The net charge inside here is 0. This excess charge is all on the outer surface. Now the distinction is we do have charges inside here, just we have as many positives as negatives, and they cancel each other out. Because we still have, it's a solid conductor, there are still atoms inside there. That means they still have protons inside there. And those protons are still attracting electrons. But it's not attracting more electrons than is needed to balance it out. So now, let's take this to the next step. I have this drawing already set. I have a thick-walled conductor right here. So this is solid, and let me do the solid part in red. So this is solid, and inside this thick-walled conductor, I have a solid conductor, a solid spherical conductor. And we throw spherical in here. Now, sometimes in wording in a textbook problem, they might say you have a conductor with a cavity, and a cavity is just a hole. The same with the cavity in your teeth. And so I have empty space in between these two. And they're somehow magically suspended this way. So, onto this thick-walled conductor here, I put -5 microcoulombs, and onto the inner conductor I put in an excess of 7 microcoulombs, so I have -5 here and +7 there. I know from the previous example that the 7 microcoulombs is going to spread out to the outside of the surface here. It's not going to jump the gap. We assume that there's not enough charge here in order to spark. And so this inner surface here will have 7 microcoulombs residing on the outside. Now, let's employ Gauss's law here. I'm going to create a Gaussian surface, and I'm going to put my Gaussian surface right here in the middle of my thick-walled conductor here. So I have a Gaussian surface. Again, it's a virtual surface. I know that the electric field inside a conductor, inside the fleshy part, inside the metal here, is going to be 0. And so, well, let's write down Gauss's law of electricity. Through a closed surface is equal to Q enclosed over epsilon sub naught. I know that the electric field inside this metal piece here is 0, and therefore my electric flux is 0. And therefore, the enclosed charge, the total charge inside my green dotted line here, is going to be 0. Well, how can that be? I got 7 microcoulombs here, and I only put in -5 there. Well, this is how you do it. So if I, again, looking at the slice here, I have 7 microcoulombs on the surface here. On the inner surface of the thick-walled conductor, I have to have 7 microcoulombs. I know that the total excess charge is -5 microcoulombs, so it pulled those -5 here, in essence. But I'm short -2, so it pulled an extra -2 microcoulombs worth of electrons to the inner surface, leaving behind 2 microcoulombs here on the outer surface. So I have 2 microcoulombs, -7 microcoulombs in the inner surface, and then 7 microcoulombs in the inner sphere, on the surface of the inner sphere. So that the total here is -5, the total here is 0. So if I wanted to find the electric field at various points, if I want to find the electric field at this point right here, we'll call this point A. Because of spherical symmetry, I can treat this as a point charge, or I can use Gauss's law, and basically we're going through the pseudo derivation that we did before. But the electric field at point A, let's give it a distance here. Let's say that this has a radius of 0.1 meters, and the inner radius here is 0.5 meters, and the outer radius is 0.6 meters. So the electric field at point A here, which is, let's say, 0.3 meters from the center, is going to be 9 times 10 to the 9th times the charge inside. I'm not worrying about the charge outside of it. There's another video out there which talks about that we don't need to worry about the charges outside of the point in question. So 7 times 10 to the -6th over 0.3 squared, 700,000 newtons per coulomb. If we then tried to find what is the electric field at this point right here, well, we could go through it in the internal, and we could employ Gauss's law, or we just know it's inside a conductor, so the electric field at this point, E sub B, is equal to 0. If I wanted to know the electric field at a point out here, and let's just say that this is 1 meter away, we'll call this point C. Then the electric field at point C is going to be, well, the total charge inside, because of spherical symmetry, the total charge inside is 7 and -5, or 2. Those cancel out, so I'm left with 2. So this is 9 times 10 to the 9th times 2 times 10 to the -6th over 1 squared, 18,000 newtons per coulomb. There'll be another video in which I talk about the transition here, that it's 0 here, it's not 0 here, what happens when you are actually at the surface itself. And that gets into some things which are really beyond the scope of the course, but at least I need to explain the hand waving.